Welcome back. I am Christopher Williams and this is FPGA Forge. In the last example, we created several logic gates and connected their inputs to slide switches and their outputs to the LEDs. In this episode, we're going to build our first clock circuit, a counter divider. The Nexys A7 has a 100 MHz systems clock, which is far too fast to see directly, so we'll divide the clock down and use it to increment a visible LED counter. By the end of this tutorial, we'll have a 16-bit counter displayed on the Nexys A7 LEDs. The counter will only increment once every predetermined number of counts of the system clock in order to divide the system clock down to something we can see increment. Once again, we will begin by opening up our base RTL project. Once we open that, we are going to add design sources. And choose SystemVerilog, and we're going to choose a name. For the name, I'm going to choose Clock Divider Top. We should see that appear here, and then we can open up our top file. We're going to start with our inputs and outputs. Input logic. This is going to be our system clock. Our output is going to be our LEDs. And for this example, we're going to need a constant parameter. And we can define that like this. This was going to be our integer that we're going to divide our clock by. This is going to be effectively 1 million. And we'll use that later. So one thing I forgot to do was to save the project with a new name. So we're going to go ahead and do that now. I'm going to call this Clock Divider, and it'll create a new project subdirectory right there. Click OK. So now back to writing our code. We're going to need some variables for our counters. I'm going to make this 32 bits. And we'll need one for our final count. Doesn't have to be as big. We're going to make that 16 bits because that's how many LEDs we have. And then we're going to assign the LEDs to the out count. And so now we're going to define our actual counter using the always flip-flop directive. We're going to increment on the positive edge of the system clock, which is defined as 100 MHz in our constraint file. I like to put an end right there so I don't have to later. So we want to increment this counter every time the clock has a positive edge. This will increment it by 1 bit. Then we need to test the count to see if it's bigger than the constant that we defined up here, the clock divider. So we can do that with an if statement. Is bigger than equal to clock divider. What we're going to want to do is we're going to clear out the main counter every time this occurs. So we'll clear out the 32-bit value with a decimal 0. And we're going to want to increment our out count by 1. And I think that wraps it up. Let's go ahead and save that. Now we're going to have to make sure that in our constraints file, we've uncommented the clock 100 megahertz and the LEDs. So let's go ahead and open up the constraints file. Clock is already uncommented. LEDs are not, so let's go ahead and uncomment those real quick. And we have saved everything, and we are ready to run synthesis. Okay, now we're ready to run implementation. Implementation is finished, and we can generate the bit stream. Bit stream's been generated, and we're going to open up the hardware manager and open the target. And program the device. There you can see the clock actually incrementing. The first LED, you can barely see it even blink. In this episode, we created our first sequential circuit. We used the 100 megahertz system clock, built a divider counter, used a parameter for the divider value, and drove the Nexys A7 LEDs with the 16-bit binary counter. This example is important because counters and clock dividers show up everywhere in FPGA design. If you found this tutorial helpful, please give it a thumbs up and subscribe to FPGA Forge. Every lesson builds on the last, and we're just getting started. Thanks for watching. I'm Christopher Williams, and until next time, keep forging ahead.